All right, welcome back. Today we're going to start looking at the second half of this unit, which is combinations. All of the lessons previous to this, we've been primarily looking at permutations as well as fundamental counting principle and factorial notation. You got a little bit of a teaser at the beginning of the unit when we did some examples just comparing and contrasting perms and coms, but now we're going to start looking at more examples in depth. And so before we get into the actual definition of combinations, I'm going to go through three different examples that will hopefully help to magnify the similarities and differences between perms and coms. So first example, it says that William and Deanna have been reading books from the Eagle Butte hit list all year. And they both have the same three books left to read, and those would be Sadie, What They Don't Know, and The Tattooist of Auschwitz. Now, in our virtual reality right now, they're probably having to think about different ways to sign out these books. But William has decided he's going to take out one book at a time. He's going to take out a book, he's going to read it, he's going to return it, and then sign out another one. Deanna, on the other hand, is a really fast reader, and she's decided she's going to sign out all three books at once. And so we're going to look at how the method of signing out those books changes our different possibilities. And so William, again, he's taking out one book at a time. We're going to list all the different orders that William can sign out those three books. And so he can sign out Sadie, and then What They Don't Know, and then The Tattooist. He could do STW. He could start with What They Don't Know, and then S&T, or WTS. We could also have TSW and TWS. So if we look at that, there are 6 different ways that William can sign out those books. Now, if we look at Deanna, Deanna's going in and she's signing out all 3 books at once. She's a really quick reader, and so she's just going to take them all at the same time. So how many different ways can she sign out those 3 books? And the answer is just one way. Because she's taking out all the books at once, order doesn't matter. And so it doesn't matter whether she takes them as SWT or STW or whatever, she still has those 3 books as her group. So there's only one way that she can sign those out. So when we're talking about selecting a set of elements, and the order of that selection is not important, we're dealing with a combination. So when we're dealing with this one here, this is a permutation or a perm, and it's because order matters. Whereas the second one here, this is an example of a combination or com, and that's because order does not matter. Now, if we look at this, Deanna was taking 3 books, or she had 3 to choose from, and she was choosing all 3, and that led us to one way. And so if we're choosing n elements, n at a time, so 4 choose 4 or 5 choose 5, the answer will always be 1. Now, this is a property that might be helpful to remember, but by no means do you have to memorize it. It's certainly something you can figure out with your calculator. Now, let's take a look at part 2 here. Suppose that William and Deanna have decided they're only going to pick 2 of those 3 books to read. And so if we look at William, again, he's signing out one book at a time. All of the ways that he could get out those books, he could take Sadie and What They Don't Know. He could take out What They Don't Know and then Sadie. He could do Sadie and The Tattooist, or The Tattooist and Sadie. Or he can take out What They Don't Know and The Tattooist, or The Tattooist and What They Don't Know. So again, there's 6 different ways that he can take those books out. If we look at Deanna, whether she takes out Sadie and then What They Don't Know, or W and then S, she still ultimately has one grouping of books that's S and W. If she does S and T or T and S, she still has one grouping of books, which is S and T. And then for the third set here, we have W and T. Again, order doesn't matter. So in William's case, there are 6 ways that he can take out those books. And in Deanna's case, there are 3 ways. And so that combination of books is dependent upon the way in which we chose to take them out. So if we look at the number of combinations and the number of permutations, the number of combinations we had here was 3. And that's equal to the number of permutations, which is 6, divided by 2. So 6 divided by 2 is 3, which is also the same as 2 factorial. So 6 divided by 2 factorial gave us 3. All right, so I'm hoping at this point you're seeing that the relationship between permutations and combinations has something to do with order. So with permutations, order matters. With combinations, order does not matter. All right, so we're going to look at part 3 here. And part 3 says that we've got 5 students, Alex, Bryson, Colin, Darian, and Eric, and they're taking part in a cross-country race to represent Eagle Butte. Now, the winner of the race is going to win $50. The runner-up gets $25, and third place gets $10. So I don't know about you, but if I'm running a race and there's a difference between $50 or $10, I want the $50 prize. For me, that's a pretty nice Starbucks gift card. So order is going to matter because the prizes are different. And so we have a table written below here. I've written out a table here. A stands for Alex, B for Bryson, and so on. And this would be all of the different ways that those prizes could be divvied out. And so the first question is this an example of permutations or combinations? Well, order matters. Order matters, so that means that this is an example of permutations. So because order matters, this is permutations. So how many ways are there to award these prizes? Well, we had 1, 2, 3, 4, 5 runners. And of those 5 runners, order mattered, so that's pick. 3 of them were getting prizes. And so 5 pick 3 on our calculators is 60. Now, a different way to look at this question. We still got the same runners running the race, but for participating in the cross-country race, the school has been awarded 3 entries for a running clinic. And Mr. Smith decides that he's going to choose those students or select those students from those who took part in the previous country or cross-country race. So we've still got the same chart here, but this time he's just selecting 3 students to go to the clinic. It doesn't matter what order he selects them, it just matters that they're going in that group. And so if we go through here, we're only going to consider different combinations. So A, B, C is one grouping of students. It doesn't matter if he chooses them as ACB or BAC or so on. It's still the same group of students. So there's only one out of that column. ABD, these are all the same combination. And I'll just go through this quickly here. You'll notice that in all cases, only the top one needs to be circled, because all the rest are just different permutations or different arrangements of the same grouping of letters. And so if we count those up, we have 10 different ways that Mr. Smith can choose his group to go to that running clinic. So in this case, order does not matter. And so that means this is an example of combinations. So if order does not matter, it's combinations. So how many ways can these 3 students be selected? Well, again, we have 5 students, just like before, but this time we're choosing them. So 5 choose 3, and that's because order does not matter. 5 choose 3 is 10. And so if we look at the relationship between permutations and combinations, it says the number of combinations, in this case, the number of combinations was 10, is equal to the number of permutations, which was 60, divided by 6. Well, 60 divided by 6, 6 is also 3 factorial. So 60 divided by 3 factorial would give us 10. Now, when we were looking at this question, there were some keywords that were jumping out. Right here, Mr. Smith is selecting the students. So that told us that it was a combination. And in the first part there, we were talking about winners winning different prizes. And so this would be an example of permutations. And so when we're looking at questions that relate to permutations and combinations, there's often some keywords that we're going to look at with regards to word problems. So a permutation is an arrangement of elements, and the order matters. So the order matters tells us that it's a permutation. So order matters. Now, if we're looking at word problems, right now the topics that you have, the title of the topic kind of tells you what we're doing. The topic's on permutations, all the questions are permutations, and this lesson's on combinations, so most of the questions will be combinations. But there's going to come a time where you're just going to be given word problems on a review, or word problems just in general, and you're going to have to decide, is it a permutation or is it a combination? In the next unit, we're going to get into probability, and it will be the same situation. You're going to have to ask yourself every single time, does order matter? And so if they tell you order matters, then it's automatically a permutation. But there's some other keywords that we can look at as well. So if you think back to those other units on permutations, we were often arranging letters. So if you're asked to arrange something or make an arrangement, that's going to be a permutation. If you're told to order some numbers or order some letters, that's going to be a permutation. If you're told or asked for how many distinct combinations or how many distinct arrangements, distinct means different, so order definitely matters. Those are all going to be some of your keywords. Now, there's also certain types of word problems that often lend themselves to permutations. If you're asked about anything related to an executive committee, this is going to be an example where order matters. If you think about 4-H, we elect a president, a vice president, a treasurer, and so on. Well, who gets those positions matters, and it's not just all equal responsibilities. So an executive committee, order matters. If we're dealing with anything to do with placing, so somebody winning prizes or placings. I think about the Olympics. If we have some athletes going to the Olympics and there's a gold, silver, and bronze awarded, order matters. So those prizes matter. So it's important that those prizes are different. Okay. If we want to look at keywords for combinations, first of all, combinations order does not matter. And one of the main keywords that we often see is selection or select. You might also see questions related to teams or groups or classes. Often you'll see questions about committees or subcommittees. Notice there's a difference between a committee and an executive committee. With a committee, it's all equal membership. With an executive committee, there's different responsibilities. So those would be some of the main words that you're going to look for, or keywords that you're going to look for. So let's delve into the specifics of a combination. So combinations of n different elements take an R at a time. The notation looks very similar to permutations. Instead of a P, though, we're going to have a C, and that changing of the letters changes the function significantly. So in those previous examples we looked at, we had the number of permutations just divided by R factorial. So that was our repeats. And so, or not necessarily repeats, but we were dividing by the number that we were choosing, factorial. And so the original formula for NPR was n factorial over n minus r factorial. So we're really just taking that formula, n factorial over n minus r factorial, and dividing by r factorial. So the formulas are very similar. These are not formulas that you need to memorize. They are on your formula sheet. All right, so the number of combinations here, we've got NCR equals n factorial over n minus r factorial times r factorial. When you're doing the function on your calculator, it's still NCR. So you're going to type math into your calculator, arrow back to probability, so just arrow left one to PRB, and then you're going to choose 2 for NCR. Now, in some textbooks and in some examples, and when I say some, I mean very few, you could see this notation here that is an N with a big gap and then an R. In all the years that I've taught Math 30-2, I've only seen this maybe 2 or 3 times, but it is possible that you could see it, and this is on your formula sheet. So if you ever see N, R, it almost looks like it's written in matrix notation. This just represents N choose R. All right, so let's take a look at some specific examples related to combinations. The first question here, it says 3 students from a class of 10 are to be chosen to go on a school trip. And the question is, in how many ways can they be selected? So the keyword right there is selected. So this tells us that order doesn't matter. We're talking about a class and we're choosing a group of students from that class. So we've got 3 students and we're choosing them out of a group of 10. So we're going to have 10 choose 3. Now this question asks us to write it in factorial notation, so we're going to use the formula from above. And so that's going to be n factorial, which is 10 factorial, over 10 minus 3 factorial times 3 factorial. And if we simplify that down, that gives us 10 factorial over 7 factorial, 3 factorial. And if we put that into our calculator, we get 120. Now, we'll go through some review of how to put that into your calculator. We're going to have 10 factorial. So 10 math back to 4 for factorial. Again, remember the part in the denominator has to be in brackets. So 10 minus, I'm just going to do, the 7 factorial, 3 factorial. And we get 120. Now, if we don't want to use the combination notation, we would type the 10 first, and then math back to NCR is 3. Oh, I think I wrote 2 before. I'll fix that. So 10 NCR 3, and that gives us 120. Now, interestingly enough, if I type in N choose 7, I'm going to get the exact same answer. Now, I'm not going to go into why that is today. I'm going to leave that as a little bit of a teaser or a cliffhanger for you. But if you can figure it out, let me know. If we were in class, I'd probably toss you a Jolly Rancher. I can't toss you a virtual Jolly Rancher, but I suppose you could have some bragging rights for it as well. So ask yourself, why would 10 choose 3 and 10 choose 7 be the same? Stay tuned. All right, so I'll change that back to a 3 there. So it was math back to PRB and then 3 for NCR. So again, if we're putting 10 choose 3 into our calculator, we're going to get 120. All right, new example. So to win the Lotto 649, my parents tell me that this is their retirement plan. I'm not so sure if that's a good idea, but it's not working out so well yet. But to win the Lotto 649, a person must correctly select, again, there's your keyword, select 6 numbers between 1 to 49. Gavin has selected 6 numbers from the birth dates of his family. So he's chosen 3, 7, 9, 11, 20, and 29. And the question is, how many different selections of numbers could he have made? So he's taking 6 numbers out of 49. So from 1 to 49, there's 49 numbers. He's going to choose 6 of them. So order doesn't matter because he's selecting them. Order doesn't matter. But of those 49 numbers, he's choosing 6. So how many combinations are there? If we put that in our calculator, 13,983,816. I definitely think my parents need a new retirement plan. All right, now think about this. This is when order doesn't matter. Imagine how many arrangements there would be if this was 49, pick 6. Feel free to test it out in your calculator, but it's a big number. All right, example number 3. So the Eagle Butte Athletic Council has decided to form a subcommittee of 7 different council members to look at how funds raised should be spent on sports activities in the school. There are a total of 15 athletic council members, 9 males and 6 females. The subcommittee must consist of exactly 3 females. So this is a criteria that they've got in place. So we have 15 council members. We're forming a subcommittee. This is different than an executive committee. A subcommittee just means that we're making a committee out of a committee that already exists. And so everybody is still an equal member, and we're choosing 7 council members. So the first question says to determine the number of ways of selecting 3 females. So order does not matter. We have 6 females, and the rules say we need exactly 3 females, so we're going to choose 6 choose 3. And 6 choose 3 is 20. Now, if we have 3 females serving on the committee, that means we still need 4 other members. And so there's 9 males, and we're going to choose 4 of them. And 9 choose 4 is 126. So how many different ways can we form this subcommittee? Well, this subcommittee is made up of 3 females and 4 males. So it's going to be 6 choose 3 times 9 choose 4, because in math, and means multiply. So if we multiply that out, we've got 20 times 126, which is 2,000 520. Now, if we add in some restrictions or some added restrictions here, how many ways can the subcommittee be selected? Again, order doesn't matter. If Mr. Grass, the football coach, must be included. So now we have to have Mr. Grass. We have to have 3 females. We need 7 committee members. There's 4 right there. That means we need 3 other males. So we need Mr. Grass, 3 females, and 3 males. Well, to choose Mr. Grass, it's 1, choose 1. There's only 1 Mr. Grass, and we're only choosing 1 Mr. Grass. And so from combinations before, we know that there's only 1 way to choose Mr. Grass. So how many females? There are 6 females. We are choosing 3 of them. And now if we look at the males, there are 9 males to begin with, but Mr. Grass is one of those males, and so we have 1 less male to choose from. So if we have Mr. Grass is 1, choose 1, and the females are 6, choose 3, the males then are 8, choose 3. And so if we multiply this all out, we're going to have 1,120 combinations. Now, if we write this out, a lot of times you might not see the 1, choose 1 because the 1, choose 1 just totals to 1. So you often will see people just write 6, choose 3 times 8, choose 3. But one of the reasons that it's helpful to write out that 1, choose 1 is because we can check that we've got everything we need just by adding things up. So if I look here, the 1 for Mr. Grass, the 6 for the females, and the 8 for the males adds up to 15. So 8 males plus 6 females plus 1 Mr. Grass makes 15 people on the committee. 3 males being chosen, 3 females being chosen, and 1 Mr. Grass being chosen adds up to 7, which is 7 members of the subcommittee. So by writing everything out, it gives us a way to check and make sure that we have included every option. And so that's going to come into play when we get into the last example. So the last example relates to cards, and no, we're not playing poker today, but we are going to talk about a little bit of poker. But before we get into talking about how we're going to use cards and combinations, we need to do a little bit of backtracking and review cards in general. Now, I find these questions are more challenging because they involve cards than because they involve combinations. So if you are not familiar with cards, I strongly urge you to pick up a deck of cards, play some solitaire, take advantage of the fact that we're in isolation right now, play some crib, play some poker, play some, okay, wait, I didn't say play poker. Play poker, but don't play for money. Play rummy, play go fish. Whatever you play, just do something that you can get your hands on some cards and you can figure out how a deck of cards is arranged. But we're going to just do a quick refresher here. So in a deck of cards, we have 52 cards. Now this is a standard deck, meaning we're not dealing with jokers. So in a 52 card deck of cards, we have 4 suits, and those are spades, clubs, diamonds, and hearts. So with 52 cards, 52 divided by 4 is 13. So that means we have 13 hearts. We have 13 diamonds. We have 13 spades. And we have 13 clubs. All right, now I purposely divided these into different colors because each suit has 13 cards, but we have half of a deck being red and half of a deck being black. That means that we have 26 red cards and we have 26 black cards. Now in each suit, our cards go from ace to 10 and then jack, queen, king. So 10 and then jack, queen, king. The jack, queen, king are called our face cards. And so face cards are considered to be jacks, queens, and kings. We have 4 jacks, we have 4 queens, and we have 4 kings. So in a deck of cards, that means we have 12 face cards. Now, poker is a game that we often talk about or hear about when we're playing cards. And so in poker, we hear sometimes about a 5-card stud. That means that there's 5 cards in the poker hand. And so the question is, how many different 5-card poker hands are possible? Well, the first question we have to ask ourselves is, does order matter? So if I lay down my hand and I show all of my cards, does it matter the order I show my cards in? And the answer is no. So order doesn't matter. So all of these questions are going to relate to combinations. So how many different 5-card poker hands are possible? Well, there's 52 cards. I'm choosing 5 of them. So that means there's 2,598,960 different 5-card hands that you can have, which is quite a few. Now, in the game of poker, depending on what cards are in your hand, it makes it a better hand. And so we're going to look at some possibilities of getting those hands. And so how many of the hands in A, so how many 5-card hands would contain all of the same suit? So in this case, all clubs. So we want all clubs. And so if we look at a deck of cards, there are 13 clubs, and I want to choose 5 of them. And from here, I can calculate my answer. I can go 13 choose 5 equals 1,287. But if you want to use that option of totaling things up, if I have 13 clubs, that means I want 5 clubs and I want 0 non-clubs. So the way that I would write that out would be 39 cards, because if 13 of them are clubs, that means 39 of them are something else. And I want to choose 0 of them. Well, the only way to have 39 cards and choose none of them is 1. So often you'll see people just write the 13 choose 5. All right, let's take a look at another example here. It says, how many different hands can we have if there are 4 red cards and 1 black card? So we've got 4 red and 1 black. Well, the 4 red cards, there are 26 red cards, and we're going to choose 4 of them. And there are 26 black cards, and we're going to choose 1 of them. So 26 choose 4 is 14,950. And 26 choose 1, there's 26 ways to choose 1 card. So there are 388,700 different ways that we can have 4 red cards and 1 black card. Now, what about 3 jacks and 2 kings? So if we have 3 jacks, that means there are 4 jacks to choose from, and we are taking 3 of them. And 2 kings, there are 4 kings, and we're choosing 2 of them. Now, if you're looking at adding up again, you might think, well, wait a minute, there is something missing here. I only have 4 plus 4 being 8. Well, you again could plug in that there are 44 cards, 44 other cards, and we're choosing 0 of them. But again, this totals to 1, so we usually don't put that in. So 4 choose 3 times 4 choose 2. 4 choose 3 is 4. 4 choose 2 is 6. So there are only 24 possible hands that would contain 3 jacks and 2 kings. So I'm sure if you were to look into the game of poker or look in the rules of poker, this is probably a hand that would be considered a higher value in the game because it's less likely to happen. All right, what's the chance of getting, or not the chance, we're not dealing with probability, but how many different combinations could we have with 3 queens? Well, we need a 5-card hand. So if there's 3 queens, that means there are 2 non-queens. So there are 4 queens to choose from, and we're taking 3 of them. And if there's 4 queens, that means there are 48 other cards in the deck. So notice 48 plus 4 adds to 52. And we're choosing 2 of them because 3 plus 2 is 5. And so that leaves us with 4 times 1,128 gives us 4,512 combinations. Okay, we've got 2 more examples here. So what if we're looking at 4 aces? Well, 4 aces is very similar to the 3 queens. So we have 4 aces here, but this time there is just one non-ace, and one non-ace. And so if we plug this in, we would have 4 choose 4. So we have 4 aces, we're choosing all 4 of them, and if you remember, 4 choose 4 is just 1. And we have 48 other cards, and we're going to choose one of them. So this is one you should actually be able to do in your head. 4 choose 4 is 1, and 48 choose 1. There is 48 ways to choose one card out of 48 cards, and so our answer is 48. Now the last question is a little bit different. It says, how many ways can we have 5 cards of the same suit? So that means 5 hearts or 5 diamonds or 5 spades or 5 clubs. So we can have 5 clubs, we could have 5 spades, we could have 5 hearts, or we could have 5 diamonds. And so we have to consider every single possibility. And if you remember from math, or means add. So it's 5 spades or 5 clubs or 5 hearts or 5 diamonds. And so how many ways can we have 5 clubs? Well, that's 13 clubs, choose 5, plus 13 clubs, choose 5, plus 13 clubs, choose 5, plus 13 clubs, choose 5. And I don't know about you, but that looks like a lot to type into my calculator. So we could also shorthand this and write it as, try that again. We'll shorthand this and write it as 4 times 13 choose 5. And that gives us 5,148. All right, so that's it for combinations today. We're going to be taking a look at combinations a little bit more tomorrow as well. And in that video, we're going to be talking about at least and at most. And so those 2 terms are going to be really important for tomorrow. Tonight, do some practice questions, or tomorrow do some practice questions. And if nothing else, get out a deck of cards, enjoy some family time with your family, learn how a deck of cards is put together. Who knows, might be a little bit of a silver lining in all of this isolation that we have. All right, thanks a lot, guys. Have a good night, and we'll see you soon.